So, okay, so I am Shouvik, and I am currently a PhD scholar in IIT Madras, working in cosmology and radio astronomy. So today I will be presenting on the topic listening to the first billion years of the big universe, searching for the 21 centimeter signal with Murchison Widefield Array. I will explain each of the terms one by one. So first billion years, like from the Big Bang to uh, now it is around 13.8 billion years after the Big Bang. So that Big Bang time started basically t equal to 0. And 21 centimeter signal, I will explain what that is, and also the Murchison Widefield Array, I will explain it later. So at the I will start with the contents. I will first motivate you. Why do you even need cosmology? Why do we are even interested in cosmology? So cosmology, as you might know or have heard, that cosmology is the study of the evolution of the universe as a whole system, and astrophysics is study of the in each individual ingredients in the universe. So in cosmology, we ask the question: how did the universe began? What are the large scale structures of the universe? How will the universe end, or how is the universe currently? What is the state of the universe? For example, if it is accelerating, decelerating, or staying constant, its expansion. And next, I will okay. So next I will start with some key insights from cosmology. Some key insights that we have come to for the past 8 decades or so. We have come to understand about cosmology, and then I will touch upon a brief evolutionary history of the universe, right? How from the Big Bang till present, like the whole 13.8 billion years, how the universe evolved. And then I will start talking about some 21 centimeter cosmology. I will explain what 21 centimeter means and how you can do cosmology with that, and what are radio telescopes. Because you people might have heard of optical telescopes, which just sees in the optical band. But I am a radio astronomer also. I use radio telescope data from different telescopes in Australia. So I will talk about that. And Murchison Widefield Array is one such radio telescope, which is located in Western Australia. And I will then just briefly mention our group's results and then conclude the talk. So at the outset, I will try to motivate why do we even need cosmology. To do that, I will ask some questions. I will ask 3 questions, and you will try then maybe try to understand how cosmology is the like it is the ultimate end goal. So let's ask the question: how do you know what you did a week ago? Like all of you, if you try to sit and remember what you did a week ago, your answer would be to probably go and check your computer's history desktop, read your diary, or try to meditate and trace back your steps. So that's how you remember what you did one day back ago. So you like these are all common sense. So you people might. Yeah. So next, I will ask you: how do you even know what happened hundreds of years ago? Like now, I'm going backwards. So from one day, I'm going to hundreds of years. So your answer would be to go and check your school textbooks, like learn about the French Revolution or the Indian 1857 mutiny or something. So you see that when you start asking questions, what happened, like in the past, your method of observation or method of what should I say? Method of inquiry changes, right? So, anyways, now like till now we have only gone till one day back and 1 week back or hundreds of years back. So now I will ask you the questions. How do you know what happened hundreds of millions years ago? For example, we know that 65 million years ago, a big asteroid hit the Earth and killed all of the dinosaurs, and then we are the species of the mammals which then started proliferating after that. So how do we know that 65 million years ago dinosaurs died? That is an interesting topic in itself. You can search it. It's basically something to do with the iridium. It's a rare earth metal which you can't find anywhere in Earth, but it is like very much abundant in space. So in the layers, geologists found that there is a particular layer in the rocks where there is a huge amount of iridium sediments, and that is found all over the Earth. So something must have hit the Earth at 65 million years ago. And they also found that in the Yucatan Peninsula, the crater of the asteroid, which was around 10 kilometers big. Anyways, so to understand what happened tens of hundreds of millions years ago, you have to either do some archaeology or dig up some stuff, look at rocks. So this is a picture from Dholavira, Harappan civilization in Gujarat, around the mature Harappan phase from 1900 BC to around 2600 BCE to 1900 BCE, the 700 years from Dholavira, and that is a very good documentary. I will urge you to see that. That is like it's available in Netflix. So up till now, I have gone to some hundreds of millions of years. But when you ask this question, that what happened billions of years ago, you see that you hit a point, because the Earth is only 4.5 billion years old. So when you start asking the question, what happened 4.5 billion years or even 5 billion years in the past, then you see that you have to leave Earth, because at that point in time there was no Earth. So you understand what I'm saying? So when you ask the question, what happened 4.5 billion years ago, there was no Earth. So you have to go beyond Earth. That's what you do. You look up at the sky. Because according to Einstein's general theory of relativity or special theory of relativity, light takes time to come to us. So the moon that you see, it was as you see 1 second ago, or the sun you see, it was as you see 8 minutes ago, and similarly, Jupiter is 45 minutes ago, and so on. So the a galaxy that you see billions of light years away, yeah, is actually how it was billions of years ago. So due to the constant speed of light and due to the vast regions of space in the universe, the farther we look back in space, the farther we look back in time. That is you all understand? Okay. So basically, cosmology is the archaeology on the largest possible scale. The universe is itself the artifact, and light is the fossil record. I have put a star because there are recent gravitational waves detection also. So light that I talk about is the electromagnetic spectrum from radio waves, ultraviolet, UV, etc., etc. But gravitational waves is an entirely different probe, which is an independent probe from your electromagnetic waves, because it probes the space-time of the universe. Anyways, so I want you to think of the Earth as a kind of a, in Carl Sagan's words, it is the shore of the cosmic ocean. So you are basically standing on the shore and you are looking back in the ocean. So the further back you look, you're looking further back in time. So that's how I try to think of it. So now I will move on to some key insights from cosmology. Basically, that's the first point I tried to drive forward. It's that light takes time to travel huge cosmological distances. I am talking about like distances like of 10 to the power of 20 or 10 to the power of 19 or 20 or 30 meters. So huge distances. We can't even comprehend that much distance. So so Andromeda, for example, is some light years away, and I will come to that later. And next, this is a introduction song from the popular sitcom, The Big Bang Theory. So you can see if you have seen Big Bang Theory, then you know the theme song to Big Bang Theory. So it starts with our whole universe was in a hot dense state. Then nearly 14 billion years ago, expansion started. So this is the theme song, you can see. So that's what it is. It is our current understanding of modern cosmology says that our universe started in a hot, dense state nearly 14 billion years ago, and it was like it was in a hot, dense state, and the universe was very young, and it was the size of the universe was small, to so to speak. Now there will be some equations, but this will be easy. So I define something known as 1 plus z as the current size of the universe, as the ratio of the current size of the universe to the size at a time t. For example, if I'm want to look at how the universe was, suppose 10 million years after the Big Bang, then I will take the ratio and I will calculate this z. Okay, and this z also is related to something known as, for example, since I am looking back in time, right? For example, if I have a galaxy which emitted its light from say 100 million years, 100 million light years, and since the universe is expanding, okay, I have not told this, but the universe is also expanding, right? So since the universe is expanding, the wavelength of light, a wavelength, due to expansion it stretches, right? So the frequency decreases. So the wavelength is stretches means frequency will decrease. Suppose a galaxy around 100 million years ago, when the universe was 100 like of its current size or something like that, 1/5 of its current size or 1/4 of its current size, when that galaxy emitted a light, the emission was at a frequency of nu emitted. Okay, but from that time till now, the wavelength of light would have stretched, right? Now this z is also the ratio of what frequency we observe the light at and what it was emitted at. So this z connects these two things: the size of the universe to the size of to the this wavelength. Understood? Or if everyone understood? So this z is an important concept in cosmology known as a redshift. Now this is known as a cosmological redshift. There is also a gravitational redshift, which I will not go into. That is basically, yeah, I will not go to that. This is called as cosmological redshift, and this basically connects your size of the universe, so to say, to the frequency of observation of any light. So now I come to the question of how do you even know that the universe is expanding, right? So in 1920s, there was a famous astronomer named Edwin Hubble. In 1929, I think, I forgot. So he started measuring. So up till that point, people only knew about the Milky Way. People did not knew that there was something like there were galaxies apart, like outside the Milky Way. So, but Hubble, he later um, um, tracked galaxies and their distances. You can like from the light that you see from the galaxy, you can track how much far it is, and then you can make this plot of velocity of the galaxy with respect to you, and then the distance. Basically, you can calculate the distance from the luminosity of the galaxy, basically, but I will not go into that. So you can, what you can do is that you can calculate the distance to the galaxy and you can measure its speed. If you want to know how you can measure the distance and speed, you can talk to me later. So this is the plot that modern from modern data we can plot, and this small red region is what Hubble's data used. So now currently we know that locally the speed of a galaxy that is moving away from you is proportional to the distance of how far it is, and this proportionality constant is a constant today, which is known as Hubble's constant, but it evolves with time. So the farther away a galaxy is from you, the faster it is moving away from you. This is known as Hubble's law. But then you might ask, why you? I don't know if you know that Andromeda is going to collide with Milky Way in the future. Then you might ask that why is Andromeda going to collide with Milky Way if I'm just telling that everything is moving apart, right? So the question is that I tricked you in the sense that Hubble's law is valid on large scales, but certainly we are here are not moving apart, right? Even a galaxy is bounded, right? So galaxies, they form a kind of a cluster. So I will come to it later. So each galaxy in a cluster is gravitationally attracted to each other. But when you look at large scales, the universe is expanding. So on top of this velocity, so a galaxy might come towards you, right? And So that velocity is added to this thing, right? I will come to it later. So yeah, keep this in mind. This is known as Hubble law. This is valid for the whole of the universe, but nearby things they try to attract towards each other due to gravity. Okay, so now I come to the evolutionary history of the universe. This part is somewhat involved, so I want you to pay attention. So this is a cartoon picture of the history of the universe. So on the left hand side we have Big Bang. So the time axis is in the bottom, and on the top is this redshift that I defined, redshift of z, 1 plus z. So z0 means today, and z infinity means at Big Bang, and time 0 is Big Bang. No, wait. So big, yeah. So this is look back time. So 13.8 billion years ago, this is t equal to 0. So what happened was that I will first try to explain it in words, then I will try to explain each of the terms one by one. I will not explain this, and we don't know about that. So I will start with this. Okay. So it helps to think of the universe as a box which is expanding in time. Now, initially, when the box was very small, first of all, this is a very loose analogy because there is a misconception in many of us that when we think of the Big Bang, we think of it as a bursting of a cracker, right, or a balloon or something like that. Like some crackers, it's in even in normal videos or stuff, NASA videos or something. You will see that there is a burst and then all of the galaxies they come. But that is not actually true because that assumes that there is a center in the universe. So that is not actually true. But anyways, you can think of it like that. You can think of the universe as a box. Okay, when the box was very small, and this is what in physics we call as an adiabatic expansion. This means that when this box increases in size, it cools. Whatever is inside, it cools. It is basically similar to when you pump your bicycle pump. You will feel that it gets hot, and when you try to do the reverse, it will feel colder because that is also an adiabatic expansion. Anyways, so this universe when it expands, it cools down, and suppose the box was very small, then the energy was so high because the temperature was so high that there was no such particles, like there were no electrons or protons or something like that. Like the energy was so high that it even broke down the protons and other particles into individual elementary components like quarks and stuff. So yeah, so later the universe started to expand, this box started to expand, and then we had uh, a universe filled with neutral hydrogen gas, because these protons and electrons, so hydrogen gas, neutral hydrogen is just a proton and an electron, right? Nothing else. So that is the simplest form of element that you can have. So after around 380,000 years or 3 lakh years after the Big Bang, the universe consisted of this box of mine, it consisted of this hydrogen gas with slightly more density somewhere, slightly less density somewhere. Okay. Otherwise, we would not have formed, because then these higher density regions, they started collapsing under gravity, and then they started forming galaxies and stuff. So this period of where you have this hydrogen gas in the universe, because initially you will have quarks and then they will form, three quarks will form to combine to form protons, and then a proton and an electron will combine to form neutral hydrogen gas, right? So that happened around this recombination period, which is this 380,000 years after the Big Bang. Okay, and then we have dark ages. What dark ages means is that there was no light in the universe. So this box of mine, it was only filled with neutral hydrogen and its density fluctuations. Stars had not formed. There were no galaxies. There were no stars. There was nothing. Only neutral hydrogen with traces of helium and other lithium elements, which was formed during Big Bang. Let's leave it like, we will only focus on neutral hydrogen. So my box was filled with neutral hydrogen with its density fluctuations and some photons, which was released during the Big Bang. and also there was dark matter which was formed during Big Bang. Okay, so dark ages means that there was no light, light in the no stars or nothing else. Are you following all of? Okay. Then cosmic dawns means cosmic dawn is what this cosmic dark age is this portion. Then what happened is that I will explain each of this term in later slides, but just giving an overview. During cosmic dawn, what happened was I told you about my box, right? So in this box, there were some places which had larger neutral hydrogen concentration and smaller like that. So where we have larger neutral hydrogen concentration, they started collapsing under gravity, and after a certain after this neutral hydrogen cloud, they reached a certain mass. They started forming stars due to nuclear fusion, where two hydrogen combine to form helium and then stuff. So and then these stars, they start emitting ultraviolet photons because the stars in their early not early career, but in their earlier in their life, they have a lot of hydrogen and they start emitting UV photons, and then they also start emitting X-ray photons, X-ray light, UV light. So this is what happened. This is neutral hydrogen, and these are all galaxies and stuff. Then these stars in the galaxies, they start they start emitting UV photons, right? So these photons, they start ionizing because my box, it contains islands of neutral hydrogen, concentration of neutral hydrogen, where my galaxy formation has started, star formation has started, and in between these islands there is also neutral hydrogen, but the density is very low. Now the the in these nodes of neutral hydrogen, so to say, there are stars, right? And they will emit photons and they will ionize the medium. Okay, I will. This may seem very over the top. I will explain it individually. And then we have this in the present day, where you have these filament like structures, right? These are where my neutral hydrogen was larger. So these are areas are what contains my galaxies, and in between these areas are known as voids. So UV photons or X-ray photons. UV photons, they ionize these voids, and X-ray photons, they started heating up this whole thing. You understand? So that is the overview of the evolutionary history of the universe. Now I will go to the details. So keep in mind, recombination, only neutral hydrogen gas in a box with density fluctuations, with the photons released during Big Bang, and some dark matter also, because we don't know, dark matter was produced during the Big Bang, but we don't know how or what it is. Okay. During dark ages, my box was sufficiently larger in size that such that this neutral hydrogen clouds, they collapsed to form. They started collapsing, and during cosmic dawn, inside this collapsed region of neutral hydrogen, the galaxies formed and then the stars formed, and later also the black holes formed also. Yes. And then these stars and galaxies, they emitted UV photons and X-ray photons, which ionized your medium. Okay. So yeah, so recombination is this rainbow-like region. So as the universe cooled, the free protons and the electrons, so the universe is expanding, right? So at first you have very elementary particles, then as the box increases, the temperature goes down, the energy goes down. So these particles, for example, initially, before this before this recombination, 80,000 years after the Big Bang, the energy was such high that the protons and electrons, even if they wanted to combine, they would have just flown away in like billiard balls. Okay. And uh, if you know class 12 in like uh, the binding energy of the electron is minus 13.6 by something. Okay, anyways, so this is what happened. So before this 80,000 years before, just when this 80,000 years after the Big Bang, initially everything was a plasma, because the temperature was so high that everything was a plasma here. So the photons, so these lines are my photons, okay? So they were like a billiard ball. So there was protons, electrons, and photons. The photons were produced during the Big Bang. The protons and electrons were also produced sometimes after the Big Bang. And these photons, they were billiard, like doing like this. Now what happened? As the time went on, the universe expanded and it cooled down. Now this electron and proton, they can combine to form neutral hydrogen. Okay, and this photon that was billiard ball, like doing zigzag motion, they can finally become free and they can just pass through the medium. Okay, so according to this, if you look far back and at a particular wavelength, you can see this whole sea of photons which was emitted at that time, right? So that is what is known as the cosmic microwave background. So this is known as the cosmic microwave background. So again, just to be clear, the photons which was released during the Big Bang, initially the temperature was so high or the energy was so high that the photons, they were the technically, if you want to know the technical term, so mean free path was very less. That just means that they were making many small collisions like that. But after sometimes what happens, that temperature, okay, so this is in temperature becomes sufficiently small such that the protons and electrons, they form neutral hydrogen gas, and these photons which was produced during the Big Bang, they can stream freely. That is what is known as the cosmic microwave background, and I have a video to show this one. Okay, so this is a video. So in a satellite known as Planck, it was launched in 2008 to measure this cosmic microwave background. Previously, also Penzias and Wilson, they measured it in 1965 uh, in an accident. Basically, they didn't want, they wanted to measure something else, but they measured this relic of the Big Bang. Okay, so let if this starts or not. My laptop is extremely slow, so sorry. Okay, it has started. Sorry. Okay, so this is an animation by Planck, and in July of 2010, the satellite went up in space, and it basically uh, scanned the whole sphere, like the 360-degree everything, and this is what they found. This is the satellite. This is a measuring region. For photon light comes and then it hits this mirror and goes into the detector. So we'll soon see. So this was launched in 2008 or 9. So it will start taking slices in a 3D in a sphere. So it starts taking slices like this. So it will cover the whole 360-degree and all the 360-degree here and 360-degree here also. So so let me say this. Okay. So it has finished taking the data, and now it will project it on a plane, right? Because this is a projection on the plane, right? I mean a sphere, yeah. Anyways, so this is what you see from the raw data, but the issue is that what I showed you before was not this, right? Because there is this huge galactic plane which contaminates your data. So this is the galaxy in optical, and then okay, then what you do, because this is what I showed you, right? And the previous video that you saw was nothing uh, similar to this, right? Basically, what you have to do is that you have to remove all the impurities. That is, you have to remove the galaxies, you have to remove the extragalactic sources, you have to remove the galactic sources, you have to remove the basically there is something known as a something electrons. There is something known as a electronic emission where inside our galaxies also, if you have a magnetic field in a galaxy, and if an electron gyrates around this magnetic field, the electron radiates. So that is known as synchrotron emission. So you have to get rid of that also. So I have another video which shows that, I think. Wait. Yeah. So this is what. Okay. How much time do I have? So this is what you saw, the whole data. So now they will start subtracting different portions to reveal the CMB. So this is the actual raw data. They will remove the individual sources. Then they will remove the radio emission from the Milky Way, the galactic synchronous emission, this gyrating the emission from these gyrating electrons. This is the radio emission they have removed. Now dust grains in the Milky Way also they emit in infrared. So we have radio, infrared, and then we have in microwave. So this is what you get, and you see that there are fluctuations, right? And these fluctuations are very tiny. In the sense, to quantify these fluctuations, so these fluctuations are so tiny that, for example, if I take the mean, if I take the average, this is in temperature, okay? If I take the average of this temperature, I will find a value. For example, I will find x. If I want to see the fluctuations with respect to the average, I will see that these fluctuations are of the order of 1 part in 10 to the power of 5, 1 lakh. So these are, so I suppose I have the mean of this graph plot is 2.73 Kelvin, and the fluctuations is 2.73, 2.50, then something. Okay, the fluctuations are extremely tiny. So this plot, it says that the universe initially, or just after the Big Bang, after this recombination, when these protons and electrons have formed neutral hydrogen, the universe was extremely homogeneous. The universe was extremely homogeneous. I mean, it is remarkable how homogeneous it was. But you need these fluctuations, right? This tiny fluctuation, 1 part in 10 to the power. Otherwise, we would not have existed here. So you need these fluctuations, and this is a intensity of the. So this is. So I say that the universe was homogeneous, right? So how do you prove it? This is what it proves. This is a. This is something known as a blackbody spectrum. I mean, so how should I explain? Yeah. So when you see this, you know that the universe was in thermal equilibrium basically. So everything was basically, if you have a gas and one part of the gas you heat it up and then it thermalizes, right? So this is what it is. So now to understand this, that yeah, in the dark ages the universe consisted mostly of neutron hydrogen, and the dark ages is during this time, okay, just after this cosmic CMB is emitted during this time. So my box, it consisted of neutral hydrogen gas with density fluctuations, and there was no light, in the sense that galaxy and star formation had not yet taken place. And then cosmic dawn, it marks the birth of the first stars and galaxies, and ending the cosmic dark ages. And they first emit UV and X-ray photons. The UV photons, they ionize the medium, intergalactic medium, and the X-ray photons, they heat up the intergalactic medium. And epoch of reionization is when you have these islands of this, like islands, and these islands of dense neutral hydrogen gas, and then voids, which is ionized. So wait, I have another video to show. Sorry. So this is a wait. Okay, so this is a so we can't see how the universe came about, right? So we can do simulations, right? So this is a particular simulation that I will show. No, I just. So this is a particular simulation I will show. So here, what you see, these bright regions are where you have higher density of neutral hydrogen, and then these are the voids, and this is a zoom in of this central region, okay? And as galaxy is going to form here, and this is a zoom in of the galaxy itself, and this is a the dark matter distribution. Basically, you don't have to worry about this. And this is at a redshift of 9.5. You can calculate at what size the universe was using this. And that is a scale, kiloparsec. 1 parsec is of the order of 10 to the power of 20 meters or so. So yeah. So you see, as the time goes on, so I told you that today was redshift 0, right? And redshift infinity was at Big Bang, right? So you see that the redshift will decrease from 9 to 0. And you see that the gas, they are coming and they're merging, right? So you have this. This is a zoomed in picture of that. And that log m is the mass of the galaxy, to so to speak, in terms of solar mass. You see that there is a galaxy forming here, right? So there are other galaxies also forming, and they're coming together, and this is known as the cosmic wave. Okay, and this is basically the dark matter, how it attracts. Anyway. So this is how the galaxies form, and so you see that one galaxy is forming there, and many other galaxies are also coming and attracting towards each other. Okay, so the galaxy has now formed. Now they will do a 3D movement. This is a spiral galaxy, you can see, and that is the dark matter distribution. Basically, I will come to that later. Okay. Okay. So this is what I had basically said. So how do you model the universe? What you say is that I told you, right, during this time. During this time, there was electrons and protons and photons, which was released during the Big Bang. I did not mention one component, which is known as dark matter. And dark matter has a whole other history, how it was discovered and stuff. The only thing to remember is that dark matter attracts gravitationally. It has no interaction using, like, you can't shine a light on it. You can't probe it any other way apart from gravitationally. So during this time, there was dark matter also. We think of it as dark matter particles. So these dark matter particles, what they do is that their main work is to come together due to gravity. Okay. Now what is happening is that in here also there is dark matter, right? So the dark matter here is already trying to coalesce together, but these photons or this matter, they also want to follow this dark matter due to gravity, right? But these photons, or there is a radiation pressure, to be honest. This radiation, these photons, they are, even if the normal matter or these protons or electrons, they want to combine, this radiation, these photons, they are not letting it to combine gravitationally, right? But this dark matter, which only interacts to gravity, it can start combining, and that is what it happens. Basically, you might ask, so our current best understanding is that the dark matter, because they can start combining early on, right? They started to combine together, they started gravitationally collapsing, and they formed regions which was very high in density. Dark matter density was high, and then normal matter, I mean this table chair, whatever it's made of, protons, electrons, etc. Since this region have high densities, the dark matters have high densities, this normal matter, they started falling into this high density region. So that is our current understanding. So this is a picture of the dark matter. So this first row shows the universe when it was 1/5 of its current size. This is when the universe was 1/3 of its current size, and this is now. So I told you that dark matter, because it had a lot of time to collapse, right? Because ordinary matter would try to collapse later, right? Because during this time, dark matter already started collapsing. Okay, but ordinary matter was prevented from collapsing because these photons, they were not letting it to collapse. There was a pressure. The photon was creating an outward pressure. This proton and electrons, it wanted to collapse, but these photons, it was creating an outward pressure, right? But the dark matter, it can collapse because it can gravitationally. It only reacts through gravity, right? Because photons does not matter to it, it does not respond. But here what happened, after this time, these photons, they were not interacting that much, right? So the pressure that was the outward pressure that the photon was creating, it was not there. So now what can happen is that the dark matter which has already collapsed, it can now start attracting the normal matter towards itself. So that is what is happening. This is a picture of the dark matter distribution. Are you understanding, by the way, or is it too much? Okay, so okay, so this is a distribution of the dark matter when the universe was 1/5 of its current size, and is it too much or is it okay? I mean, I know it can be a lot, but yeah. But basically, you have to know this, that dark matter, they don't interact with anything. They don't interact with photons or anything. They only interact through gravity. And initially, also, that dark matter had a lot of time to collect itself, and then yeah, initially the normal matter was not able to not able to coalesce gravitationally, because the photons, it was creating a radiation pressure outwards, and then after this time, the photons were free streaming, right? Because neutron hydrogen formed, and during that time also the dark matter had collapsed enough such that normal matter can start following this gravitational potential well, so to say, to fall inside. This is what the picture is. So here you can see that this is dark matter distribution, and this is normal matter, and this is temperature. And you see that the as the gas, neutron hydrogen gas, it starts to fall inside this dark matter high density region, it starts heating up. This is temperature, right? It starts heating up. So you see that there is a lot of green here, and this is a zoomed in. You can see that there is a galaxy that is formed. And later on, different dark matter blobs, you can see that there are small, this region, it has content small, like the orange points are there, but there the intensity is low, right? So the dark matter itself can combine to form bigger dark matter halos, to say. And when they form bigger structures, the gas itself, they start following into this dark matter region. And that is how this circle is increases, because this is the dark matter halo, to be honest. It's you can think of it as a sink, as a like a container of dark matter, which inside which the ordinary matter is falling, and also the dark matter also is falling, is attracted, right? So wherever there is more dark matter, much more dark matter comes inside, and this my container, it increases in size, right? And as it increases in size, since this dark matter region is already a high gravitationally bound region, normal matter also comes down. And as normal matter comes down, this whole potential energy is converted into this kinetic energy, right? This in suppose, so for example, if in a waterfall, the water at the top and the water at the bottom, there is a temperature difference, because there is a high potential energy, and then it is converted into kinetic energy of the water, and then it falls. So if you measure the water at the bottom, you will see that it has a higher temperature than at the top. Same thing. So here the neutral hydrogen gas is falling. It is falling into this container, okay, so to speak, and it is getting heated up. That's how you have a galaxy. And then different dark matter halos, they have different galaxies and they combine. So you have this galaxy cluster. So galaxy clusters form, and then you have stars formation in galaxy clusters. So this is now how that was a model, right? So how do we even know that it is our model is true? So basically, this is what I show you. Every point here is a galaxy. So what you do is you send a probe out and you measure each galaxies, and this is what you find. I was telling you, right? This thing, there is this filament-like structure, there are voids. This is what it is. This is actual data from the DAISY survey. And you are here, oh, you are here, and this is like this because this is the Milky Way plane, right? So you want to see above the Milky Way plane. So you're seeing like this. That's why it is like this. And you're seeing back in time, right? So this, if this is a Milky Way plane, you're seeing like this and back in time. Understood? So every point here is a galaxy, and these color coding are just for different galaxies. And I have a video of that also from Daisy. Oh. So every point here is a galaxy. So you can look above the Milky Way and under the Milky Way also, right? So these are the two bands. And there are these are every point is a galaxy, and this is the most detailed galaxy survey ever. This was released, I think, 2 months back or so. So yeah, you can read the thing. So Daisy, so Earth is at the center of the animation, and you're seeing above the Milky Way and below the Milky Way, and each point is a galaxy. What this Daisy survey, Dark Energy Spectroscopic Instrument Survey, Daisy survey, is what it measures is it measures the galaxy position, XYZ, and the galaxy velocity. You remember I told you about Hubble's law, how Hubble measured the galaxy velocity with the distance. Same thing, you can measure the galaxy velocity. You can ask me later how you measure the galaxy's velocity, but I will not explain it here. So every point is a galaxy in here, and this was taken using the dark energy spectroscopic instrument mounted on the 4-meter telescope at this National Observatory in US, basically. And this is the result of Daisy survey. You can search it. There are amazing pictures, and this is the most detailed map of the universe. So as you can see, our universe consists of this filament-like structures and these voids, right? Which I explained above. These filaments have higher concentration of neutral hydrogen, and each of these nodes, they contain galaxy clusters, superclusters. I will come to that later. Are you following me, everyone? So these are known as this. If you search cosmic wave, then this is what it is. Okay. Apparently, so one thing I find very unique about nature is that if you see brain scans, you will say that the brain is also something like this. Like brain has also this neuron connection like this. So like it is a like same kind of thing. So if you see brain scans or like yeah, so it's like the cosmic brain or something like that. And so this was so I can see like this, and I can see at a distance, right? In the next, this was in a data release 1 in 2018, and then in 2026 or 2025, they saw even at high distances. So they increase. So this region was what we saw here, and this is the whole depth. Understood? So how much time do I have? Okay, so now you know that this we are here, and then this is a cosmic wave, right? So now I will focus on the nearby, because I told you, right, there are galaxies, one galaxy is there, and there are this cluster of galaxies, right? These are known as local clusters or cluster of galaxies. And then when you have these galaxies are all bound by dark matter. So dark matter, I told you, right, dark matter potential, well, their galaxies are bound. So this is what we see. So this is the local group of galaxies. This is our Milky Way galaxy, and this is a galaxy cluster. So our Milky Way galaxy is here, Andromeda is there, and these all galaxies are bound in a dark matter halo. So they are all gravitationally bound together. So what happens is that, suppose for example, in very how should I put this, very rough language, or not rough language, very loosely, each galaxy has its own dark matter halo, and when you combine different galaxies, you form this galaxy cluster, and this galaxy cluster, they are bound together. Okay, so this is Milky Way, this is Andromeda, and they are basically orbiting together, and this is known as the supercluster. And these clusters are all these nodes I'm talking about, or these things, these nodes, or these nodes. Okay. So this is the galaxy Lanaika supercluster, that was local group. So the local group is here. So the local group itself contains galaxies, and then many such local groups, they groups of galaxies, they form superclusters. And these superclusters, they are those nodes in your cosmic web. The nodes are the regions of high density. Then you have a filament, and then another node and a filament and another node. Right? In between there are voids, and these voids are what are ionized. Okay, I told you, right, the UV photons ionize the intergalactic medium. So this is the intergalactic medium, or this is the intergalactic medium which was ionized by these UV photons from these galaxies. Okay, are you following me? Okay, is it boring? Is it exciting? I don't know. Sorry. Oh, so this is a zoomed out picture. So that is Earth, solar system, outer solar system, where you have the Oort cloud, from where you have the this. Have you heard of this extra interstellar object Oumuamua or something like that? Three of them have come. 3I Atlas is coming, and there was this big, huge thing of, I think in February or something, that will hit Earth. So it was from interstellar space, right? So yeah. So there is this. This is the solar system, and there is this Oort cloud which has asteroids. And then when you zoom out, you go to the local group. You go to closer stars. So our sun is one star. Then you zoom out. Then you go to the local stars. There will be Proxima Centauri, Alpha Centauri, etc., etc. And then you zoom out. Then you see that we are here in the one arm of the Milky Way, right? Then you zoom out. You see that we are here. This is one cluster, one cluster of galaxies. There is another cluster that is known as Andromeda, and each of these are bound together, right? I told you that there was Hubble law, right? The galaxies are moving apart. V is equal to hd. But then I said that nearby things, they come together, right? So these are these are gravitationally bound. So when you zoom out, you see that this whole local group is a small part in this, a small tiny dot. Then you are a part of this Lanaeka cluster, the Lanaeka supercluster. Then you zoom out, then you have Lanaeka supercluster here or somewhere. So you have a cluster of superclusters. And then when you finally zoom out, you have this universe. Okay, I will show one video which will probably make things in perspective better. So this is a video which shows. Okay, sure. Sorry. This is a video which is simulation, which is a flyby through the universe. You see that they are these bright regions. They are your nodes basically in your cosmic web, which contains superclusters, clusters, and then look. This is a flyby of the Millennium simulation. You have these cosmic voids and this cosmic web, and yeah, and these are voids and the webs. So it's basically this. So everything is a galaxy cluster containing billions and billions of stars. And some nodes are larger in size, some are smaller in size, and there are filaments like that. So this is one big node with the filaments, and there will be a large number of superclusters here with containing billions of galaxies, like that. Yeah, I mean, yeah, this will zoom in, and yeah, it will zoom in on the galaxies and stuff. Yeah, it will zoom out. Yeah, now I can show you one thing. Should I show this because it's 4 minutes long? That's what I guess. You can. I will share it with Siva if you want. Everything is available online. I mean, yeah. And this is one such simulation. This is the this is one snapshot of the whole cosmic web, right? You see that these are all the voids. These are the nodes where your density is high, with superclusters and cluster stuff. And this is on a scale of 1 gigaparsec. So I can tell you what gigaparsec is, what 1 parsec is. How to explain 1 parsec? So you know this parallax, right? Have you heard of parallax? So parallax is like if you put your arm like this, and if you see it like this, it will see like this and like this, right? So we have binocular vision, right? So we can focus on it. So what you do is that, can I get a pen? So you can talk about light years or you can talk about parsecs. Okay. So for example, this is your sun, and this is a star. Okay, and this is Earth, and this is Earth after 6 months, right? Now, when you see from here, you will see it like this. You will see it here, and when you see from here, you will see it like this. You will see it here. So two eyes looking at the same thing from different positions, and you can measure the distance from the sun. This is known as this is how you measure distances through parallax. Now, 1 parsec is, so you have 360 degrees in a 1 degree you can write it as 60 minute and 60 second, right? 1 degree in a protractor, for example, you can divide a degree into 60 minutes, right? And 60 seconds. 1 parsec is the distance at which you have to keep an object such that your this parallax angle, it is 1 by 360th of a degree. It's a huge distance. So extremely tiny fluctuation. Understood? So basically, you have to keep your finger at that point such that this parallax is 1 by 360th of a degree. You can understand how far it should be. Okay? So that is, and gigaparsec is 10 to the power of 9 times that, even further. So it will zoom in. So this is all the universe on that scale. Now it is zooming in. So from gigaparsec, 10 to the power of 9, 1 billion parsec, we will go to megaparsec, 1 million parsec, and then we will zoom in. So you see that these are all the filaments and these are the galaxy voids, etc. Understood? This from a, so yes, so this is for example a particular filament, and you see the scale is increasing, but the scale is decreasing. You zoom in on one thing and then yeah. Okay. So so this brings me to the whole observable universe, and now you have heard of JOWST, right? I have a lot to say. How much time do I have? Oh, thank you. Okay, so tell me if this is too much, then I will take a break or something like that. Yeah. Then you know that JWST was released recently, right? And JWST is a very sensitive instrument, the James Webb Space Telescope. So I told you, right? We have observations of the universe at this cosmic microwave background, right? This thing, which happened at that time, and then we have observation which I was showing you at this time, right? This was observation. Now we don't know what happened in between. We don't know what happened. So that's what I am trying to motivate. So we have observed the universe when it was very young, the cosmic microwave background. The universe when it was around 385,000 years after the Big Bang. And then we have observed the universe when it is relatively old, the nearby galaxy, this thing, whole thing, right? This whole thing. But we don't know what happened in between. We have some of JWST is bringing up some clues, and it is probing the high redshift to, so to say, further back in time. So here it is what it is. So you can focus on the top plot, forget the bottom plot. Basically, this shows the star formation rate or how quickly star forms in redshift. You can forget this. So this is important. Here on the x-axis you have the redshift. This is now time since the Big Bang, 1 billion years. This is now. This is earlier, right? This is present time. This is earlier time. This is present time, earlier time. And in this top panel, the y-axis, on the top it shows bright galaxies, and on the bottom it shows faint galaxies, right? So top means bright galaxies, lower means faint galaxies. This is earlier in time, that is backward in time, like towards now. Okay. So you see these orange plots. Oh, sorry, these blue plots, these blue points are individual galaxies that has been measured this far back in time. You see that is very small in number, right? And only the very bright galaxies are measured and till of sufficiently for some distance back in time, right? But after JWST, if you see this orange plot, you will see that the around 1300 galaxies have been measured, and the whole it goes up to a like when the universe was uh, like 290 billion years after the Big Bang, right? This one. So with JWST, you can observe further back in time and even faint galaxies. But the problem is, wait, but the problem is that this creates a bias in your data set, because whatever inference you draw or whatever uh, theory you conclude, there will always be bias of your telescope, right? Because your telescope can only see up to a particular noise level, say up to a particular sensitivity, because your this JWST it has a sensitivity limit, right? It cannot see beyond that sensitivity, otherwise it would be comparable to noise. So that is one caveat that you have. So you are biased with this, because JWST has observed galaxies up to a redshift of 14, say, which is around 300 billion years after the Big Bang. But they have observed only the bright galaxies, very bright galaxies. So whenever we make a model or a theory out of this, that will have an inherent bias in it, because you will be only biased towards the very bright galaxies, and you might uh, think that the universe was ionized by these bright galaxies only. That will create a bias. So what to do now? So there now comes the 21 centimeter cosmology part. To do that, I will first go to radio astronomy. So everything I've talked about is in this range, gamma ray. So this is where Hubble operates. This is where Hubble operates. This is infrared, near infrared, visible. So wavelength is increasing that side, frequency is decreasing that side. So gamma ray is very short wavelength, so high frequency, and X-ray is also high frequency, and microwave is low frequency, for example. And these are all the telescopes that are currently available or in future. And this is the whole electromagnetic spectrum, right? And this is gravitational waves. I'll not go to this anyways. So I will be interested in this radio, right? Because one thing is that you can watch radio waves from Earth, because radio waves are not attenuated or they are not blocked by the atmosphere. Near infrared is attenuated by ozone layer, and optical also. This is the, or should I say, transparency or opacity as a function of different telescopes. So you see that sitting on top of the Earth, you can see the visible part. That's why you have these optical telescopes, right? And you can see the radio part. Your uh, gamma rays you can't see, because the atmosphere it absorbs the gamma rays. The oxygen or the ozone in the atmosphere it absorbs the infrared, and long wavelengths are basically blocked because uh, they reflect back and come. Anyways, and this is the image of the famous M87 in 2018. You must have know that the first black hole image was published, right? So that is M87. M87 means Messier 87. Messier was an astronomer, French astronomer, I think, maybe. He made a catalog of things in what he saw. So it is a big catalog. So M87 is Messier 87 in the Messier catalog, 87 number. So M87 is a galaxy. That is an optical image of the galaxy, and that thing you see, that is a radio or a jet. So uh, you have this AGN, or the active galactic nuclei, which inside a galaxy. So the galaxy is there. Have you seen Interstellar? Okay. So you have a galaxy inside the galaxy, in between, at the center of the galaxy, you have this AGN, or the active galactic nuclei, or the black hole. So as the things fall inside this black hole, they are they are radiated outwards, and these are the jets that you can see. That is in optical, and this is the central black hole, and this is in radio. So you see, this is the galaxy. There is a lobe of radio jets, which is 4. So this is scale, like this is 4,000 light years, and this is also that. And this is a zoomed in picture of this region. This is 2,000 light years, and this is the basically the black hole in radio. and that is in optical, the same black M87 stars, and that is not in optical, this is in radio. This is also in radio, but that is a different kind of radio. That is the yeah, like that is using a VLBI basically. Anyways, so that is optical. This is radio, and that is the picture of the black hole at the center. Understood. So, and this is an image of the galaxy, Circinus galaxy, as seen in different wavelengths. So you have the cold hydrogen cloud. So this is the neutral hydrogen cloud that I was talking about, right? Because galaxies, they need neutral hydrogen to form, right? And this is the warm dust which emits in infrared, and this is the stars in optical. So if you superimpose these three images, you get that. You see, only optical, it does not give you enough information. You have to go to other wavelengths also. So now it comes. So now I told you about radio telescopes and stuff. So the thing now, my question is, or the point I'm trying to drive is that suppose. So I told you, right, during cosmic dark ages, neutral hydrogen was present everywhere, right? So neutral hydrogen was present all of the time, right? Even in galaxies also. And there is this peculiar thing about neutral hydrogen. The ground state of the neutral hydrogen, you have a proton and an electron, right? Proton and an electron, right? And there is something known as spin. So for example, if this is up, this is a higher energy state. And if this is proton, this is electron, okay? This is a higher energy state. If it flips down, there's something known as a spin, okay? There is a quantum mechanical effect. Just think of it as pointers. This is a proton's pointer of spin. This is an electron's pointer of spin. And this is a higher energy state. They don't want to be together like this. They want the stable configuration of the lower energy state is like this. Electron spin is down, proton spin is up. So when you do this, you change the energy, right? This is higher energy, this is lower energy. So then what happens is that through quantum mechanics, or if you look at it through quantum mechanically, a photon is emitted. Wait. This is up, this is up, down. So the energy difference corresponds to a photon. So the energy difference, when it flips like this, a photon is emitted. The wavelength of the photon is 21 centimeter, corresponding to a frequency of 1420 megahertz. So yeah, you can forget this. I mean, interaction between the magnetic moments. Yeah. Basically, these two spin, they interact, and this thing is the lower energy state, and the energy difference is corresponds to a wavelength of 21 centimeter. And now the thing that I want to say is that this neutral hydrogen, you remember, was everywhere, right? Right from the Big Bang till now, everywhere there was neutral hydrogen, right? And the universe is expanding. So this 21 centimeter signal from the neutral hydrogen, which was emitted during this time, will redshift through the formula that I showed you, right? So I know that at that point in time in the universe's history, this 21 centimeter was emitted by the neutral hydrogen, which when it has come to me will be not in 21, not in centimeter, it may be in meter wavelength or something like that. So like this, if I have a observation and I know that it was released from the neutral hydrogen, and if I see that it has the wavelength of it is 20 meters or say something like that, or 200 meters or something like that, then I can say that at which time in the universe's history it was emitted, right? Yeah. So with this line, so I told you, right, there was this dark ages, right, when there was no stars and stuff. Stars started here, right? So JWST, which observes optical or near infrared, it can at most go till here or something like that. Because it cannot go beyond the point where there were stars, where there were no stars, right? But this 21 centimeter, it was emitted by this neutral hydrogen all throughout. So if I can measure this 21 centimeter signal from this area, this time, I can make maps, right? maps of the universe of different times. Because, for example, if you send a signal 21 centimeter, I will receive it as 21 centimeter, right? If he goes farther back in space, then the 21 centimeter it will get stretched, right? So then I can suppose I'm sitting on the Earth like a hemisphere, right? Or the wavelength that I observe, I can trace the whole history of the universe like this, right? Because this 21 centimeter signal is coming from everywhere. If I measure it and I see that it is at a wavelength of 210 meters or something like that, I can make the map of the universe at that time like this. Understood? So I will basically be able. That is like an FM radio tuner. So I can tune the radio and I can go back and forth in the universe's history. Okay. So that is ideally or theoretically that what it should be. Okay. So yeah, so I can skip this. Yeah. So basically, what you can do is that with this 21 centimeter, you can make maps of the universe at different times in its history. So basically, you can make slices of the universe. You can make a box of the universe. You can see slices of the sky at different point in time. Understood? So yeah, you can make this kind of boxes. And yeah, but I will skip this also. I will skip this also. But the problem is that I am talking about the universe when it was at this point, right? At this point, right? From here to now, a lot of things has happened, right? So if I want to see that far back in time, there will be all of these things in front, right? And I told you that any wavelength, it can expand and it can come into this range, right? So that is known as foregrounds. I will, sorry, my laptop is very slow. Sorry. Yeah. So this is the cosmic dawn or the epoch of renunciation signal that I want to measure in some units, millikelvin, for example, in temperature units. You can make a conversation, but let's say it's in some units, intensity. But in between that time till now, there is a lot of things that has happened, right? There are extragalactic foregrounds like black holes or AGNs, extragalactic AGNs, or there are many galaxies out of Milky Way, right? Which contains they emit their own uh, emissions, and then there is the galactic foreground, the Milky Way foreground. They also emit in the same frequency range. So combining everything, you get that. So it is extremely hard, or no one has been able to do it. No one has been able to measure the signal at that far back in time. You can measure this in the nearby universe. That's how you can measure it in the nearby universe, right? That's how you get this thing. This is the because this is you are mapping this the cold hydrogen gas, right? This is basically the neutral hydrogen gas, and this is mapped through 21 centimeter. So in the nearby universe, you can map it because there are no like it is not contaminated enough. But when you go farther back in time, there has been a lot of things in the middle. The whole universe has been ionized. So it is no one has ever yet detected it. No one has detected it. No one. And these are the some of the experiments that are measuring this, trying to measure the signal. So you can measure it in two types. For example, you can look at the sky and you can average the whole sky. That is one. These are that kind of experiments. So you have one. This is known as EDGES, and this is in RRI in Bangalore, Raman Research Institute, where this is the SARAS experiment, where they basically float this antenna, horn-like antenna, radio antenna, on a pond, lake, such that the reflection, the backward reflection, it is less, because if you place it on a ground, the ground can reflect back, right? But if we place it on the lake attenuates the infalling radiation. And then you have space-based experiments. So this is a proposed experiment in from India known as Pratyush, and this is also led by RRI, Mayuri S. Rao in Raman Research Institute in Bangalore. And that is a planned NASA experiment which is supposed to place a radio telescope in the crater in the far side of the moon. Now, why far side? In 1973, this experiment they observed the RFI or the radio frequency interference. Radio frequency interference is everything apart from the signal. Sorry. So even in your phone also talks in radio frequency, right? Your FM phone, everything. So when you're trying to measure that signal, you don't want this, right? So what this telescope or this satellite measured that it orbited the moon, and this is the noise level or the radio frequency interference, so to say, level when it was in the side of the moon facing Earth, and then when it passed to the so these are different frequencies from 25 kilohertz to 13 megahertz. When it passed to the through the far side of the moon, you see that the radio frequency interference is almost zero. So the far side of the moon is very radio quiet. So it blocks the all of the radio frequencies from the Earth. That's why China, India, and everyone is so like hell bent to plant or probe the far side of the moon. So if you can set up a telescope on the far side of the moon, then you'll probably observe the signal or do some experiment. And there are radio interferometers or radio telescopes on the Earth as well. And this is in Pune, 990 kilometers from Pune. This is known as the GMRT Giant Meter Wave Radio Telescope. And this is in Lofar is in Netherlands. This is in Hera. This in Hera, and this is the square kilometer array. This is going to be the next biggest thing in radio astronomy. This is going to be a huge project, and I can't emphasize enough. Like this will be a huge endeavor. India is also a part recently. The NCRA National Center for Radio Astrophysics in Pune. They with the government the government has officially funded this project, this international collaboration SKS Square Kilometer Array. And this Murchison Widefield Array, this is the data set that I am working on. This is a radio telescope. Okay. Now I told you, right? Suppose I tune my telescope such that it observes at a particular wavelength, and I know that the 21 centimeter it was emitted at a particular time at 21 centimeter, right? And so, for example, the data set that I have, I'm looking at all those wavelengths which are 2 meter in length. Okay, and I know that at the 21 centimeter was emitted at 21 centimeter. So I know at what redshift it was emitted, right? So the data set that I'm working with, the telescope, the data set that the telescope has took, it is at a 154 megahertz, which corresponds to a redshift of which is at a redshift of this around this epoch of reionization. This okay. So the data that I'm taking from this telescope, it is from that region of the universe as history, that portion. But again, that will contain 21 centimeter and all those foregrounds. So the data, it is composed of everything. So I have to clean the data. That part is extremely hard to do. No one has done it. Okay. So this is one of the telescopes in Western Australia. So here you see that there is this hexagonal structure. Each structure has this. Each structure is made up of this 4x4 16 dipoles on a wire mesh. So this is 4 meter across 4 meter, and there are 16 dipoles. So a dipole is like this crossed. So one measures this. So electromagnetic wave, it has polarization, right? It is like this, or like electromagnetic waves have polarization. So it is either like this or like this, anyways. So it can measure two polarizations. Yes. So one of these bow tie like antenna is this. So it has different uh, dipoles. So one, two. So this is one. This is two. Like this. So this can measure one polarization of your electric field, and this measures another electric. And this is one. I In electrical engineering, for example, you have this antenna response thing, where you know how what is the sensitivity to your of the antenna to different regions in the sky. Similarly, this is a radio telescope, so this has a particular sensitivity, and this is the sensitivity plot. So your telescope is most sensitive to this region, and it is less sensitive here, and it changes with frequency. I can show you a video. So this is a how the sensitivity of the telescope changes as a function of frequency. So you see that that is more sensitive, and then you have like the contour it changes, right? These are interference patterns basically. I won't go into that. So your radio response, telescope response, it changes with frequency. Okay. So the frequency that I am interested in, wait, I'll just do one thing. Let's just wait, I will just show you. So you can see what, right? Just remember this thing. I told you that I am taking observation at 154 megahertz, which places my observation at a particular time in the universe's history, right? At that frequency, this is how the telescope's response it looks like. So the telescope is most sensitive to here, and then there are these nulls basically, interference thing basically. So the telescope beam it looks like this. There's a huge lobe, and there are side lobes like this. So okay, so this will be important later. Just remember this. So this is why it is important. So are you following, or is it making you feel sleepy or something? This is my research actual that what I'm doing. So that is your telescope's beam at that frequency, right? And this is your sky in some coordinates. So this is the Milky Way, and your the telescope is like this, and the sky is drifting. So this telescope is stationary with that beam pointed up like this. The telescope is sitting like this. The beam is pointed up with all these lobes and stuff, and the sky is drifting. That this is in that same picture. This is the Milky Way plane. This is a telescope central lobe, and these are the different lobes. And this is the center of your telescope. And you see that the observation it starts since the sky drifts, right? So you can start. So this was taken. Data was taken in 2016. So the observation started at 2:30 p.m. Then the sky drifted for 5.5 hours, and then it ended. The observation ended, right? So the observation starts here. So the observation starts. The sky drifts. Sky drifts, goes. Observation ends here. So this is the zoomed in picture. So the observation starts here. It crosses this region and it ends there. And you see that at the end of your observation, you have this bright radio source, which is known as Fornax A. It is a it is a kind of galaxy which I showed earlier, right? Wait. It is a galaxy of this kind. It is basically a double lobed galaxy, which I showed earlier. The M87 galaxy that I showed. Uh, Do you remember I showed you the central black hole, and then there was a jet-like thing, and then here was a radio. I don't know where it went. Anyways, I don't know where it went. Oh. Yeah. So you see that there is a central galaxy, and there are these two lobes like structure, right? So this Fornax A thing is also that kind of a galaxy. So it is a double lobed structure like galaxy, and it is very radio bright. So this comes, and my central frequency is at 150 megahertz, and at a redshift of around 8.2. So that places my observation in that region of the universe's history. And then what I am trying to measure is so this is my last slide. Sorry. Uh, Bear with me. This is the timeline of the universe. Okay, this is earlier in the past. This is now, almost now. Okay? As you go from here to here, the time increases basically. So you're looking back. This is far back in time, and what you're interested in is known as something known as the power spectrum. I will explain what that is. For example, a question that you want to ask, because I told you, right, the universe consisted of these filament like structures, right? So all of this filament has a particular structure, right? So you want to know, to give an analogy, for example, you see the earth from above, and you want to know how many city like structures are there. So what you will do, you will measure, for example, if you define a city as a building and a building with a particular distance, you will fix your distance, you measure different uh, buildings like this, right? And suppose if you say, now if you want to say how much power is there at different scales. For example, if you want to see the for example, if you see the ocean, right, there will be small waves, there will be large waves, right? So you want to ask the question, how much power there is at different scales. Similarly, if you want to ask the question, how much structure there is at, for example, continent scale, city scale. For example, when you see the Earth from above, there will be, of course, much large more cities than continents, right? There are 5 continents or so on, but there will be many cities, right? So if you plot the power, so the cities, so the city has a somewhat scale, right? So this scale corresponds to a city scale, and this corresponds to a continent scale. So if you want to know how much structure there is in the earth in city scale or in continent scale, and you plot it, then you will see that the city scale, it will have higher power. Basically, there are a lot more structures in the earth at city scale. For example, even if you ask uh, how much power is there in a, for example, random scale, I mean, for example, a car scale or something like that, then that power will be even larger, right? So the same thing I'm asking here. I'm asking how much power there is in this cosmic web at a particular scale, as a function of universe's time. Okay, this is a very convoluted concept, but this is basically what it is. Like, you're asking how much power there. You look at the universe at that redshift, or I can directly look at, but from the data I can do something and I can try to look at, and I can say that I can try to ask the question how much power there is, how much structure is there is. For example, I gave the analogy, right? City scale. So this is what it is. The y-axis is the power, and at a particular scale, you have fixed a scale, and that is the power as a function of your time. Okay, so you are seeing that, and these are all measurements from telescopes. So we have only upper limits. You see that there is a point, and then so we say that, for example, this is the lowest upper limit. So what we say is that at this scale, when you look at the universe as it evolves in time, when you see the power at this scale, you fix the scale. The power at this redshift, this far back in time, cannot exceed this. Understood? This will be a, this is a very, this is actually my research, so this will be a different. So that's what it is. Like you're asking how much power there is at a particular scale at a particular redshift. So my data set is at 8.2 redshift, 151 megahertz. I told you, right? So it places my measurement here. Okay, and this is my point. At this redshift, this is the maximum power. So you can't have power power in the 21 centimeter signal up above this. So that is my this is basically my paper that was published in recently 2-3 months back. So yeah, this is from this paper, and this is the conclusion. So the 21 centimeter line is a unique probe of the cosmic dark ages and the cosmic dawn and the epoch of regeneration, and no one has been able to measure it. So we are only putting upper limits. No one has yet measured the 21 centimeter signal. And measuring the signal will allow us to probe the structures, how structures formed, etc. Because I told you, right, the whole universe has neutral hydrogen right from the beginning. Stars formed later, even galaxies formed later. And detecting this signal is extremely challenging due to all of this thing that has happened between that time and now. And the Murchison Widefield Array is one such telescope which is posed to measure this signal at that redshift, basically that far back in time. And the continued advances in observation, data analysis, and upcoming instrument will bring us closer to the universe, to revealing the universe's first billion years. So thank you for the talk. Thank you for the listening. So any questions? I don't know how much I got through, but oh, this limit. Basically, we try to subtract out what we know from the data set that we get, and then we compare with simulations, and then say that my pipeline, if I work it on this data set from the telescope, and if I work it on this 21 centimeter, pure 21 centimeter signal simulated, how much signal I lose, then I can know that, okay, so beyond this I am losing signal, so the signal strength must be above this. So I can talk with you later if you want. Yeah, any other questions? By the way, this thing that I was explaining, I mentioned, I told you, right, this lower plot, I told you this was bright galaxies and faint galaxies, right? And this was time, and this is star formation rate. Basically, the higher up you are, the higher star formation rate is. So the JWST, what is telling is that, you see from these blue points, as a function of time, the time goes back, right? JWST was telling that the star formation rate was falling as you go past in time. But no, Hubble was telling that the star formation rate was falling, these blue points. But JWST has now come and said that it was constant. So that is a very interesting thing. Basically, this is the plot, the same plot. This is the redshift and star formation rate. This is what we used to believe, that there was a peak at a particular time in the history, and then it went on. But JWST is saying that it is going like a constant. So we don't know why that is, and there should be, yeah. This is one of the, yeah. Nothing. Thank you for listening, and I hope this was enjoyable. And I don't know. Yeah, just shoot it away. Yeah, ask me questions. I mean, did you understand the basic of how the gravity collapsed everything? And this last part is my research, so it might be very. This last part is my research. It will be very difficult to understand. But did you understand the dark matter halo and how it fell in, and how the temperature of the gas increased, and how stars formed? That is the main thing that I wanted to convey. If that is clear, then it's okay. Because many people ask me how this cosmic microwave background was emitted. I tried to explain it how it was emitted. And another thing, tying back to the start, I mentioned that when you think of Big Bang, do not think of it as a point like a cracker bursting and then things expanding. No, because universe do not have a center. Because when you think of a cracker bursting or a firework bursting, you think of a center, right? So the universe did not have a center. I can explain how it went, but so that's it. Thank you. Any questions?
So, basic question out of curiosity. The space is very vast, right? I mean, even the Milky Way is very small.
Yeah, yeah, yeah.
So we keep hearing about UFOs, aliens. Uh, anything you know around that? Is more interesting.
I mean, look, there are. I showed you the scale, right? There are so many. Our Milky Way, even our solar system. I told you, right? Just to give you a perspective, I sorry. Just to give you a perspective, right? This is our solar system. This is the outer solar system, and so uh, so this is sun. So this is the Earth, Milky Way, Earth, solar system, outer solar system, and this is the sun. There are all these other stars, and then you see that we are just here. This is sun. Then you see that even this also is there, and there's Andromeda. Then you see that also is here. Then you say that this also is here, and then you say that this also is that. So we are here. So this whole thing is here somewhere. So the universe is filled with stuff, stars, and planets. So there is a very interesting and exciting field that has been taken, that is recently developed, which is known as planetary extra planetary sciences, exoplanets. Yeah, what they look at is that they try to find exoplanets, and then there are many. JWST has like boomed the recent observation, and there are many exoplanets that are being found. I mean, there are exoplanets with like which are made of diamonds and like diamonds like diamonds rain and stuff like that. There's sulfur and stuff. Yeah. So the universe is a very wild place. I mean, extremely wild place. I have not touched black holes actually. Like, that is also extremely wild. I mean, there are places in the universe where the neutron stars, for example, they rotate like 500 times a second or 500 hertz. So that is a whole star rotating, and then there are black hole mergers and stuff other than that. So the universe is an extremely interesting place. So yeah, I mean, a lot of things are going on. I mean, and then there are stuffs like this dark matter we don't even know. This dark matter, what is holding these galaxies together, we don't even know. And then I have not even touched about dark energy. Dark energy is different. Dark energy is what is causing this acceleration of the universe. So dark energy and dark matter are different. So we don't know what that is, and we don't even know in the cosmic planetary scale also. For example, there is a very interesting talk about a planet 9, which is somewhere beyond Neptune or beyond Pluto. Like and its orbit is large. You can search it in the net. Planet 9. That is yeah. That's one. Yeah. So I am a data analyst. I have a data from the telescope, and I'm trying to analyze it with different techniques and stuff. And actually, no, this is publicly available data. But this was taken in 2016. So the usual rule is of thumb is that, for example, in GMRT, the radio telescope in India, that is a radio telescope. For example, if you so I our group, we write proposal for the telescope, for proposal for time on the telescope, and we get. I've been to GMRT and I've observed it for like late nights and stuff. And in for GMRT, the proposal group, they have the proprietary of the data for around 2 to 3 years. After that, it is made public. So this data I'm working on was taken on 2016, so 10 years back. So now it's public, and even JWST data, or you can apply for the telescope time and stuff like that. Yeah, there is a site actually. I can, if I don't have the internet, but you can search NW Murchison Widefield Array telescope data archive. You will find the telescope archive. So it's public data.
How's the data been in the morning times? I mean, like this.
Morning sign of the sun, right? You have the sun, and also morning time of the sun. Morning time you have the sun, and since this is so in GMRT when I went, so I'm talking about GMRT, not the MW. You know, you saw the GMRT, right? The big dish in India. So when I went there in 2024 to take data, it was a different data set that I went. So there they said that my observation started from around 8 p.m. in the night, and it went on till 4 in the morning or 5 in the morning, and I used to sleep there anyways in the control room. And we choose night because in the morning there is this sun plus there are other, because people are awake in morning, right? So they do stuff and they emit lot of radio frequency interference, and also
Not all of them your interest in the wavelengths in your frequency interest.
yes, you have to, yeah, you when you get the raw data you have to calibrate it. Yeah, you have to calibrate it because there are all this if you plot the time versus frequency, because for example, if you have your phone, it emits at a particular frequency, right? So if you plot the data as a time and frequency, your phone's emission will be at a particular frequency for all time. For example, suppose there is this Pune Nashik express or expressway, there is this train line near GMRT, and you see the electric locomotive, it has a pantograph, right? And it hits this wire. So when it hits the wire, there it creates a spark, right? So a spark is a superposition of many frequencies, right? Because it is a, because you're confining it in time, right, and space. So you have to superimpose a lot of frequencies. So that is a broadband spectrum. So if you plot frequency versus time, that your phone will be a line, and this spark will be a broad but at a particular time. So it will be like this at a particular time. So that is a line spectrum or something like that. It will be a line. Satellites will be a line, frequency versus time, and this spark will be a, at a particular time. It will be a broad line because it encompasses a lot of frequencies, right? So that's how we can tell. So these are, so basically I'm dealing with clean data. So cleaning or calibration is another process because you also have to deal with Earth's ionosphere, right? So you have to subtract Earth's ionosphere and subtract out different things from the telescope's data. Raw data, like people's PhD theses are on raw data. I'm getting calibrated data and I'm working on it. So someone else calibrated the data and did his PhD. So that's,
Completed your PhD or
huh?
completed your
No,
PhD?
no, no. I officially have 1 year left. Yeah, I officially have funding for 1 year. That's,
So how you were interested in doing this kind of work?
so see, I was always interested in cosmology. I, because I told you right from the start, I asked 3 questions. That how I got into this thing, because I was interested in dinosaurs. Before that, I was interested in history. Then I started asking questions. Then I went back and I saw geology. And then I came to understand that after 5 billion years, you have to go to cosmology. And then, and I came here, and my guide was he joined new, and I was also his first student. I have not talked about because there are many people in my department who work on the. I told you right, Big Bang, and there was inflation, right, and then there was recombination. I completely skipped this first two. Big Bang we don't know nothing about. Inflation we have theories. Some one person in our department he works on this, because in inflation the universe started from a pea-sized and it expanded by 10 to the power of 60 in 10 to the power of minus 32 seconds. So the universe expanded. I don't remember the exact scales, but something, it expanded this size in seconds. This is known as inflation. That I did not talk about. So that is a theory. We don't have proof of it, but this theory, because you see the CMB, right? You you know that it is very homogeneous. So you start asking the question, why did the universe start in such a homogeneous? Why was the universe homogeneous to begin with? And this is one of the theory that tries to explain it. Because you hit a screen, right? Because CMB is like a censorship. It because Big Bang and then you have the CMB, right? And the CMB is acting like a censorship. So as if the universe is not allowing you to see the Big Bang. It has made a screen. So the only inference that you can, so it's like a screen, and behind the screen something has happened, and the imprint is on the screen, and you have to infer things about what happened on from the screen. That is known as inflation. Like that is the theory of inflation tried to explain it, and I'm not an expert in that. That's why I skipped this these two. We don't know what Big Bang was. People, there are string theories and other stuff. They say some things, and there are many. In even for inflation also, there are like 40 models or something models like that. So yeah, I mean, what we can do now is that we can observe the CMB, because I showed you the light, right? Because light also has polarization. Because polarization experiments are going to be the next phase in this observation. Yeah, and also there during Big Bang there was gravitational waves, and these gravitational waves, they will also have imprints, because gravitational waves are produced. Electromagnetic waves is this electromagnetic spectrum. Gravitational waves are produced when you perturb the space-time itself. Like when you have a, for example, you have a black hole or black hole neutron star merger. They merge and they have such a strong gravity that they emit ripples in the gravitation space-time itself. So those are gravitational waves. And during the Big Bang also there would be gravitational waves, and though their imprints would also be in the CMB. So there are upcoming experiments which will try to observe the CMB also, but I'm not an expert. Thank you for.
Thank you for
Yeah,
this amazing talk.
thank you, Siva, for inviting me.
Yeah, we have a little something for you.
Thank you all.